Intro. In this video we are going to study the centrifugal chiller, a chiller that uses the centrifugal type compressor to compress the refrigerant. On the screen we have the animation of a chiller of this type where we can observe the process of its operation. We observe how the heat that enters the water from the water that we are going to cool causes the evaporation of the refrigerant inside the chiller cooler. That refrigerant that is originally in a liquid state, product of heat, evaporates at an almost constant pressure and gains heat from water. That refrigerant in the form of vapor reaches the centrifugal compressor that we are seeing in the animation. An increase in pressure occurs and it leaves through the discharge of the compressor towards the chiller condenser. This chiller that we are showing in the animation is a water-cooled chiller, which means that the heat that was gained from the frozen water, the water that we want to turn into frozen water, that heat that was removed from the water, we must send it to the environment. For that we use a heat exchanger that is the condenser, and the condenser we are going to cool it with water. The Triceratops is a compressor that we are going to see in already high-capacity chillers. It is a compressor that bases its operation on the increase in pressure by speed. The components of such a compressor are the impeller, diffuser, and volute. The impeller is in charge with the rotation, with the rotational movement of increasing the speed of the refrigerant. By increasing the speed of the refrigerant, we are providing energy. That energy, then, we must convert it into energy in the form of pressure. This is done with the diffuser, all this inside the ball. The refrigerant flow, the refrigerant vapor, which comes from the evaporator, enters through the center of the impeller and gains speed with rotation and then leaves with the same impeller at a high speed, and through the diffuser we are going to convert that speed into pressure. That is, the procedure is to gain speed with rotation and then with the diffuser to convert that speed into pressure. By the principle of conservation of energy we can explain that when we have an increase in speed and through a diffuser we convert the speed into pressure, we are then doing the refrigerant compression. In the animation we can see how the compressor works. The regulation of the flow of this type of compressors when they do not work at 100% is by varying the input of the amount of refrigerant that will enter through the center of the incluser. In this way we can regulate that more refrigerant enters or that more refrigerant enters depending on the thermal load we have. Let's remember that it is very important that the chiller can work, that it can maintain a good performance at loads below 100%, because statistically it is known that most of the times the chiller works is below 100%, so the compressor has to be regulated. It has to be able to adapt to what the application is asking for. That is done by the centrifugal compressor of this chiller that we are studying. Varying the radial inlet of the refrigerant that comes from the evaporator in this way will also meet the demand. On the screen we have the complete chiller cycle. We can observe how we have two temperatures or two pressures in the circuit. We have a high pressure above and a low pressure below. We are going to observe how the temperature we are observing the temperature of the water that we are going to freeze, that is the temperature of the water that we want to freeze, that we want to condition at a low temperature, enters at 55 degrees Fahrenheit and leaves at 45 degrees Fahrenheit. For a differential of 10 degrees Fahrenheit. Now if we go up and talk about the water that is going to cool the condenser, we have an input of 85 degrees Fahrenheit and a water outlet of 95 degrees Fahrenheit water temperature. We note that the two temperature differentials between inlet and outlet is 10 degrees Fahrenheit. However, the flow rates of the evaporator and the condenser are not the same because the amount of heat that we must remove in the condenser is different from the amount of heat that we are going to remove in the evaporator due to the heat gain from the compressor. On the screen we are already observing the pressure and the temperature not of the water but of the refrigerant. The refrigerant will always have a temperature lower than that of the water. We are observing it at 44 degrees Fahrenheit. For a pressure on the manometer of 39 psi. With this value we are guaranteeing a certain differential with the water to be above the freezing point, which is close to 0 degrees Celsius. So we are going to keep the pressures above 30 psi to ensure and avoid freezing of the ice water. We see that the refrigerant comes from the expansion. It enters the evaporator and through the heat that is removed from the water that we are conditioning the water, that this difference that we are seeing in temperatures in the water, that heat passes to the refrigerant. The refrigerant with that heat begins to boil. This process practically occurs at constant pressure. It practically occurs at constant pressure, and in this way we are extracting the heat and we are reaching it at an almost constant temperature and pressure in the refrigerant, but not in the water, because the refrigerant is in two phases. Then it can maintain its thermodynamic properties practically unalterable while the water is in a single phase. Any gain or loss of heat will be manifested in its properties. Now we have on the screen the condenser that is going to be in charge of passing the heat that we remove from the frozen water, the water that we want to bring to a low temperature. Now we have to send it to the environment. For that we are going to use an additional circuit, because this chiller that we are seeing in the animation is a scientific chiller whose condenser is cooled by water. We have the pressures that we are going to handle in the facility, and we have the temperatures that we are observing. Notice that 85 degrees Fahrenheit is the inlet water temperature and 95 degrees Fahrenheit, the outlet temperature. We have 4. It must be remembered that the advantage of water-cooled condensers is that they work at humid Volvo temperature, which is very good for performance when we are going to install the chiller in places where humidity is lower. So these water-cooled condenser chillers have a very optimal performance. So we have two factors that will greatly increase the performance of this unit, because we have the centrifugal compressor, which in itself is a compressor with a fairly high performance, and we also have the evaporated cold condenser. If this chiller, which has a type of compressor, can be adapted to partial loads, we will have an installation with quite optimal performance.